Hello, welcome back ladies and gents. Lecture number 10, integration revision for year 13s. I didn't actually put there year 13s. Today we're going to look at questions 104 to 115, I hope. The list is up here. Without wasting any time, let's go. Integral number 1, or rather integral number 104, shall I say, on this list is the integral of 1 plus, sorry, that's wrongly written, 1 plus the cos of 2x dx. Okay, there are two ways we can do this particular integral. Both are acceptable. I'm going to show you both. It's fairly tough. Both methods require specialized techniques. Version number 1. This is the one I would probably use for something like this. I'm looking at the denominator, and the denominator has a cos of 2x. And even if it was a cos of x, more advanced people can actually use exactly the same technique. Just try it. So I'm going to put the bracket on the denominator, and I'm going to use the identity for cos of 2x that gets rid of the 1. So that's going to be a 2 cos squared x minus 1 dx. The ones will cancel. So what I'm going to end up with is 1/2, that's the 1 over 2, and the cos squared at the bottom is very nice because of course it is simply a sec squared of x dx, and therefore this will be simply a half tan x plus c. Nothing else to write. Very, very simple once you spot that. There's a second way of doing this particular one. A lot of people for this type of scenario, they multiply top and bottom of this integrand. They try to create basically a difference of squares. So if you look at what we started with, and of course this works with a lot of other integrals. So 1 plus cos 2x, 1 minus cos 2x, because of course this will simplify now. And it will simplify to, I'm going to write here, that's a difference of squares, or you can take your time and times it all out. It's going to be 1 minus cos squared of 2x. And of course, that simplifies further. That's the whole point of this, is actually sine squared of 2x. So this is our denominator. So I'm going to write it now as 1 minus the cos of 2x. That's a numerator. And all of this, I could have written line upon line. It will be, of course, the sine squared of 2x. Split your fraction. 1 over sine squared of 2x. I like to write it as a cosec squared of 2x, because that's an exact differential. Cot differentiates to minus cosec squared. And a cos of 2x over a sine squared of 2x is two ways it can be done. I'll show you both actually. It's the first integral. We can waste a bit of time, I guess, perhaps in the beginning. I won't be doing that if we're close to the end. So one way we can deal with this split, let me write it first of all. And I'll show you two variants, because we're now advanced enough perhaps to follow both methods. Okay, first of all, d by dx of cot of x is minus cosec squared of x. So this is that, but we have also a chain. So one version of that, this comes from differentiating a cot of 2x. We need a minus because of what we got in there, and because of the chain rule, times 2 divide by 2. So that's integrating this term here. Now this second term, I've gone through it under trigonometric integration. It needs to be written, I'm going to write it up here in red, as cos of 2x over sine of 2x times 1 over sine of 2x. Why do I want to do something like that? It's because this expression now simply is the cot of 2x. Let me move this paper a little bit further to the right. Hopefully it will stay there. That's the cot of 2x cosec of 2x. And why do I want to do something like that? Because of course the differential over cosec d by dx of cosec x is minus cosec x cot x. Sorry, I cannot fit it on the same line. Okay, so according to that, that is the same as that, which is the same as that. Of course, if you're just doing your work, please don't do as I'm doing on the board. I'm trying to economize in board space and rubbing afterwards. So I'm now looking at this line here and I'm integrating. And of course, that's an exact differential. So that comes from differentiating a cosec of 2x. Cosec produces a minus, and I do have a minus. It's not there, but it is there. So I need to start as a plus. It also produces a times 2 because the arguments are 2x in there, and therefore I need a half to cancel it, plus c. So this is the answer to this particular integral. There is a second version. I'm just going to do this bit here separately just to show you. Some people see it very, very differently. They'll get the same answer. Just look at this integral for a second. That's for the people that are a little bit more advanced. Sine squared of 2x. One way is to split in a multiplicative sense, create cots and cosecs, and it's all done. But there's another group of people that see things a little bit more complicated things rather. So they can write this as follows. They write that as minus, let's use some brackets, cos of 2x, that's this bit here, and this I'm not going to write as a cosec squared on the top. I'm going to write it as a sine of 2x to the power of minus 2 dx. And this, of course, is a reverse chain rule. Is the sine of 2x powered up and its derivative next to it. So how we integrate that? Well, that's a higher power of sine. This is quite advanced to see, so if you're not following this, please ignore it. Just put me on mute for a few minutes. Okay, so sine of 2x, increase the power by 1, is going to be that. Careful, that's not an arc sine. Arc sine, the sine to the minus 1, which I'll never ever use and should never ever use it. It means a very different thing. So that's sine of 2x all to the power minus 1. You differentiate that, and minus will come to the front. That's good. Also, the power will go to the minus 2. All good. It produces, of course, the cos of 2x, which we have in there, and it will also produce, of course, a minus 2. So we have everything except this 2. The minus, of course, I should really rub it off because it's not there, and therefore we need a half in front of it, plus c. And if you look at this line that I've just written in there, it's, of course, the same as a half cosec of 2x. Was this integral hard? Is that a hard integral? The answer is yes. If you're being given that on a standard A-level exam, I can actually see this particular question causing major problems. And I hope, I cannot think right now what kind of hints I could give you. Perhaps for something like this, perhaps you ought to be said by using your double angle identity for cos of 2x or something along those lines. This pen is now well and truly dead. Let's get him out of the circulation because I keep using the same pens and I never throw them away. So this is now 105, and the integral is 2 over 2x minus x squared. The first time we see this, it looks quite strange. You say, wow, I've never seen things like that before. What do I do in there? This is just partial fractions. It's just that the multiplied as a very simple scenarios, not two brackets, and that stops you from seeing what's going on in there. If we pull out an x and then x, sorry, not x, writing stupid things, 2 minus x with a 2 on the top dx. This is now something which we can split. Let's take this pen out and this pen out because they're dead. Okay, so we can do the side workings for partial fractions, or we can just do it by cover up or by inspection. If you're not confident or if you haven't seen anything like that before, I will advise against it actually, is to do your workings. I'm not showing workings here, I'm just going to give the answers. So I'm going to put x and another 2 minus x here, and I'm going to fill the tops. If x is equal to 0, I'm getting there 2 over 2, which is 1. And if x is equal to 2, I'm also getting 1. So this is the split for this particular partial fraction. So I always check, even if I do cover up, just to check that it's all good. X minus x cancels, and then I got 2, so that's all correctly done. And that's 2 simple logs. That's the log of mod of x. And then careful here, because we've got a minus. So from the chain, log of 2 minus x plus c, which of course you could have written as a single log altogether. So the log of x over that, or you can swap this one because it's modded. So this is number 105. 106 coming up. Is 106 hard? The answer is no. It's a standard technique. Let's see if you recognize it. So 106 is the integral of log x over x squared dx. Okay, how do we integrate that? This is integration by parts. We normally see products in integration by parts, but we can think of that, of course, as the log of x times, if you want, 1 over x squared, or probably better, as x to the minus 2 for us. So this is how I do my integration by parts. I'll do a little grid, a sorter. If we have logs, the log always goes to be differentiated. I'll put it on the top left, and the x to the minus 2 to be integrated. So log of x differentiates to 1 over x, and this comes from the differentiation of this quantity here. So my answer is always equal to the product of this, so minus x to the minus 1, you could have written as minus 1 over x, times, I'm going to get out of the way, I'm being careful because this mic is always on my feet, and an accident will happen live very soon at this rate. Log mod of x, you actually don't worry about the mod there if you don't want to put it, minus the integral of this diagonal, so that is going to have another minus from this bit here. And then if you look at what these two things are, you can think of that as being x to the minus 1. So when you times them together, it'll be x to the minus 2 dx. And very quickly, let's kill those minuses into a plus. And this will integrate to x to the minus 1 with a minus at the front plus c. So you can write a little bit different or a little bit better perhaps with your indices. Let's keep ticking the ones we've done. That was 106. 107 coming up. Let's see if you recognize the technique for 107. Integrals now will become a little bit more involved, but I started speeding up as well because hopefully we will have better skills in integration to actually do a lot of them. So this one, I'm not going to give any clues. Let's see how many are going to spot it straight away. dx. What do we do with something like that? Is it hard? Is it easy? Okay. It's, well, partial fractions maybe break this denominator. It actually can be factorized, strangely enough, but it's actually completely mad to be doing stupid things like this. Okay, for something like this is the technique bottom differentiates to top. So when you're having integrals which look like this, the answer is always the log of your denominator. And this one does not even need any sorting out, any adjusting with numbers. X cubed plus 1 differentiates to 3x squared. And of course the answer for that is the log of mod of x cubed plus 1 plus c, with nothing else to say. Is there another way it can be done? The answer is yes. The substitution, if you don't spot that, I hope you just resort to the good old friend substitution. And if you use this substitution, it works really well, very, very quickly. So that's done. We got integral 108. We've done quite a few of those in the previous lectures, the last couple. 108. Need to copy it correctly. 2x plus 1. 2x plus 1 over 2x minus 1 dx. How will we integrate that? First of all, Long divisions, what is advised by most teachers at schools. All good, it works. Some teachers also say use a substitution. The substitution, use your denominator, will also work. But for me personally, something like that, I'm going to manipulate it and divide it on the spot. So this is how I do it. 2x minus 1 in a bracket, and a 2x minus 1 in a bracket on the top. So this will split that divided by that. But of course, that's okay for the bottom, but that's not okay for the top, because of course, they're not equal now. I've got 2x plus 1 and a 2x minus 1 in there. I need to balance it. So in order to be worth the same, I need to add 2. And that's exactly the same. I'm not putting extra lines of work. 2x minus 1 divided by 2x minus 1 is 1, plus 2 over 2x minus 1 dx. And that integrates instantly. 1 integrates to x, and this is just a log mod of 2x minus 1. It also produces a times 2, but conveniently we have a 2, therefore it has coefficient of 1 plus c. Integral done. Number 109. I don't want to really do this one, but is it because it's hard? No, it's because it's tedious, this particular one, and I think we've done already another one of this type today, so not 2 of them in one lecture is too much. 109 is the integral of 14x plus 1 over 1 minus x, and 2x plus 1. Let me just check plus and minuses because I make mistakes very often. 14x plus 1, 1 minus x, 2x plus 1. Okay, we should be able to recognize it. It's a little bit of work. It is partial fractions, of course. So we do it by cover up or a full method. I mean, it's not difficult to do. It just takes a few 3 or 4 minutes or whatever, probably less, to actually do the partial fractions. Let's do it by cover up. So if you haven't seen cover up, let me just explain a little bit actually what I'm doing in there. Maybe I should do a lecture on this particular technique, or just generally partial fractions. This is what my partial fractions should split. So what I do, I need to free my hands from loads of pencils for the time being, so because I'm going to need that hand to actually show you what's going through my head. I'm looking at this expression here, which I'm trying to split, and I'm looking at this fraction. What value of x makes this 0, makes it disappear? And quite clearly, the answer is 1, okay? So if I put x is equal to 1, this will be gone. Then I'm looking at the rest of what I've got left with, and I'm looking, of course, at the bit I covered in here. If I put 1 into the rest, I'm going to get 14 times 1, which is 14, plus 1, which is 15, over 2 times 1 plus 1 over 3. This will be the coefficient of the 1 minus x, the one that I just covered. This is a little bit hard, perhaps, the example I picked, because the numbers are not very pleasant. Now I'm going to fill this bit. I'm covering the 2x plus 1. What value of x makes this disappear? Quite clearly is x is minus a half. So I'm filling this one, so I'm putting x is equal to minus a half in here. What I got left is minus a half times 14 is minus 7, plus 1 is minus 6, over minus a half in there, 1 minus minus a half is 3 over 2. And this will simplify. Normally I'll be doing this in my head, depending how numerate you are or whether you're using a calculator. We got 5 over 1 minus x, that's the 15 over 3. And this is going to be a minus first of all. And 6 divided by 1.5 should be 4. 2x plus 1. And I'll always check afterwards. It's not difficult to check that this does work. So if you look at what I'm doing in there, I'm going to have 5 times 2x is 10x, and minus 4 is another 4x from there, 14x. And then the numbers, I'm going to get 5 times 1, 5, minus 4 is 1. It's correctly done. Okay, so after that we are going to just finish him off. So that's the log of mod of 1 minus x, or if you prefer x minus 1, it doesn't matter, but it still has a minus at the front, and of course the 5 which is there. And this one, mod inside the log 2x plus 1 times 2 to be created, minus 4 divided by 2 is minus 2 plus c. Question done. As I was just saying before we started this is a little bit tedious. Partial fractions, they're easy, but I don't like them because there's no real skill involved in those, and they're kind of mundane, and just say, oh no, not one of these again. Okay, number 110. Number 110 is 6x, integral of 6x over the square root of 2x plus 3. Checking if it's correctly written. Yes, it is. Dx. How can we do this particular integral? It's no bottom differentiation to top, no partial fraction, no trig identities. You can actually do integration by parts. I wouldn't recommend it by writing it as 6x times this bracket to the minus a half. It's okay, it will work, not my cup of tea. The standard way of doing this is by substitution. You use either u is 2x plus 3, or u is the entire square root. Both of them will work. I'm a square root man, and I tend to use this particular version most of the time because this has a little bit more work to start with, but it actually in general gives easier results. Of course, it can be done by inspection as well, which I'm going to show you. So I'm going to use the second substitution. U is the square root of 2x plus 3. If we use the square root substitution, we must square before we differentiate. It's advised, strongly advised in fact. Then we differentiate implicitly. So 2u du by dx, you should have done implicit differentiation before you've done integration in general in most schools. So this, if it doesn't make sense, just ignore it and use the other substitution that I gave up there. And this differentiates to 2. U du, the 2's will cancel on both sides, is equal to just dx. So my integral now will become, let's leave the 6x for the time being, let's leave him alone for the time being. We're going to have a u, I call the whole square root u, and my dx is u du. So this will simplify to 6x u over u du. The u's will cancel, and is that good? Careful, because mistakes can happen under exam pressure. People integrate their 3x squared and they're happy. Of course it's not, because the integration with respect to u, and these are x's, so we need to get the x's. The x's are not difficult to get. Take this line, 2x is equal to, move the 3 to the left, u squared minus 3, and probably triple it there. So 6x, because we got 6x up there, is equal to 3u squared. What am I doing? I'm tripling, minus 9. So this will give us now 3u squared minus 9 du, and this will integrate to u cubed, and u cubed is minus 9u plus c, and my substitution, if you want, that I used up there, is of course the same thing to the power of a half, and therefore this will be u 2x plus 3 to the power of 3 over 2, that's the cubing this bit here, minus 9 lots of 2x plus 3 to the power of a half plus c, and the question is done. If you didn't follow the square root substitution, the other substitution has very similar workings. It's not that bad, but that's the sensible way of doing this question. For those who are heavyweights, I have shown how to do integration by substitution without doing substitution. It's more of a show off, and I would not advise to be doing this in an exam. I'm going to show you basically how to split the fraction without actually doing any substitutions. We need to create on the top the same thing, that 2x plus 3, and from the 6x I'm going to put a 3 at the front, and I'm going to put a 2x right at the bottom as 2x plus 3 to the power of a half. So at the moment it's exactly the same. Add 3, close bracket. I've just added 3 in there. Now take away 3 to balance it. dx. Split your fraction. We've got 3 on the other side. That divided by that will give us 2x plus 3 to the power of positive half minus 3. That's shifted to the top. 2x plus 3 to the power of minus a half dx. And you've got 2 linear adjustments now to do. 2x plus 3. Increase the power, goes to the 3 over 2. Differentiate it. So that's going to be 3 over 2 times 2 is 3. And at the moment, I'm going to have a third in front of it. Let me just put the extra line in there, and I'll times at the end. So that's a third. Of course, it would have been nothing because of that 3. And now we come into this one. 2x plus 3 to the power of positive half. Now we're increasing by 1. Differentiate to adjust. Half times 2 is 1. 3 divided by 1 is, of course, the same. Plus c. And if you multiply, this will give you 1. And this will give you minus 9 as we had before. I don't want to write it, but I hope you get obviously you have the answer from before, and you can compare it in your own notes. Okay, 110 done. 111. I think that's not bad. I prefer to do integrals like the 111 to partial fractions anytime. I don't like also integration by parts. That is not because it's hard. It's because I don't know. It's something about it. We all have our favorites. And we have also our dislikes, our personal dislikes. So 111 is integral of sine to the 4 of x plus cos squared of x divided by sine squared of x. A trig integral, some identities, some splitting. Lovely that we have a single item on the denominator there. I'm going to split it without showing workings, of course. Sine to the 4 divided by sine squared is sine squared. That does not integrate instantly, but I know how to integrate sine squared with special identities. And cos squared over sine squared, it gives me a cot squared. Cot squared doesn't integrate either, but that requires its own identity to do it. You need to remember now how to do sine squared and cos squared. We haven't done one of these for a little while, so I'm going to write some stuff down. Sine squared and cos squared equal and equal, or I should say identically equal. The sine is a half minus a half cos 2x. The cos is exactly the same, but with a plus. These identities for me and my students it's a given. They learn them and I know them by heart, but there's nothing but rearrangements of your cos of 2x identity. If you rearrange that, you get those two. This is needed to integrate sine squared and cos squared. The cot squared, of course, you need to use this identity. And the reason you need to use this identity is because the cosec squared is an exact differential. We use it today, I think, already. It's because d by dx of the cot of x is minus cosec squared x. So let's do things a little bit slowly perhaps for this one. Sine squared x. We write it in this form first of all. Identity. By using this line here. Now both of these things integrate. Cot squared. 1. Actually, mistake in there. It's not 1. I'm using this identity, rearranging to get your cot squared as cosec squared cos x squared x minus 1 dx. And I'm going to save myself a line by putting the two numbers together. The a half minus 1, they're going to make this into a minus a half. And I begin my integration. Minus half x from this term here. To get a cos of 2x, I need to differentiate a sine of 2x. Sine differentiates to a plus, and therefore the minus that I see there must have been there from the beginning. You also produce a times 2, so I need to divide by 2. So the half will become a quarter. Lastly, I need to integrate that cos x squared of x. Cot differentiates to minus cos x squared, so I must have started with a minus cot plus c. And this is my answer for integral number 111. Is the 111 difficult as an integral? The answer is for the typical student that sits A levels. It can be quite stressful having to integrate trigonometric expressions like this. It's not hard if you know your stuff. This is a gift. It's 3 lines and you're playing with it, but it's too many identities, too many differentials which require trig bits which are not standard, and it can cause problems. Number 112. Number 112. Now this has mixed techniques, almost certainly. So let's write the integral. What do I mean by mixed techniques? I mean it needs more than one thing in order to integrate. It's not just a single thing like integration by parts. Probably we haven't, I think we've done only one question so far that had substitution followed by integration by parts. So this is the integral. What do I do with something like that? First of all, please, I've seen this before. Do not do this. Okay, this doesn't work. You'll get an A and a B, believe it or not, but they're gonna be absolute rubbish. Pants. It's not good. You need to have linear expressions at our level to sort of like do partial fractions. We cannot do partial fractions for this. Okay, so don't do it. So what's the problem with this integral if you think about it? The problem with this integral is this square root of x. I want to get rid of it. And the only sensible way to get rid of something like that is to use a substitution. U is the square root of x. Square it first. Differentiate with respect to x. So 2u du by dx is equal to 1. Or this one, you don't even need to do this because you can write it backwards. And then you can do dx by du if you prefer it. So you're treating that as your x, so it's 2u. And then when you rearrange it, you get dx is 2u du. It's exactly the same thing you would have got from if you'd done implicit differentiation. So what happens to this integral now? Let's start transforming it. The x minus 4, what is x? X is u squared, so this will now become u squared minus 4. That's this bracket here. The square root of x, I called it u. The 2 is on the top. Let's make this a little bit shorter. And my dx is 2u du. 2u du. Is that good? First of all, let's write it a little bit simpler to make sure we don't miss anything by mistake. Often in work, I've done it myself, not because I don't understand what I'm doing. If you write it very, very messy or scribbles or whatever, I have cancelled in the past a U with a U from a DU. Not because I don't know what I'm doing, I promise you, just bad handwriting or rushing. So let's simplify it, that's okay. We can cancel a U, which makes it a little bit better. And now we got 4 u squared minus 4 du. Question is now, what do we do? What is that thing? Well, the difference of squares are telling me this will go into partial fractions. Nice partial fractions. Okay, this I know by heart, this particular partial fraction, because it occurs very often. But we're going, since I've done one cover up today, I might as well do one more to actually show you the technique. This is in fact a lot simpler. Okay, we're trying to find here the coefficients, your A and your B basically. Let's put the du at the end here as well. that will make this work. I cover this bracket here, the u minus 2, into a plus. The plus 2 will make it go away. And I put u is equal to 2 into the rest. So this will go 4. There's a 2 in there. 2 plus 2 is 4. 4 divided by 4 is 1. Where's that 1? On top of this. I'll do the same thing now with the other bracket. What will make it go to 0 is minus 2. So I covered it, so I'm going to find what goes in front of that. If I put minus 2 in there, minus 2 is minus 4. 4 divided by minus 4 is minus 1. And if you want, I can put it at the front like this. So that has actually split nicely into two simple partial fractions. And this will now give me the log of u minus 2 minus the log of u plus 2. No change, no nothing, no coefficients, all good. And perhaps is better, I'm going to do two things at once. I'm going to put it onto a single log, and at the same time don't forget to put my x's back in, and my u stands for the square root of x, so that should be the square root of x minus 2 square root of x plus 2 plus c, and this is my answer for integral number 112. And I hope you followed it. It's a substitution that goes into partial fractions. That's what I meant when I said this is mixed techniques. Is that hard for exam purposes? I think that is actually not that bad. I mean, somebody who's targeting perhaps a grade A or even a grade B by today's standards should be able to cope with something like that without assistance. Number 113. That is a lot harder. I'm only going to do it one way, and I'm going to do it the best way, but I'm going to tell you what's another way of doing this. It's a variant, actually, not another way. It's kind of like just slightly different. But if you do it in this way, I will explain to you what is the snag. Copied it correctly? Yeah. All right. What's the problem there? What technique is there? I mean, this now looks very, very messy, very scary. Why is it scary? Quite clearly this. That's what makes me very scared. So quite clearly, if I'm very scared with something like this, we can make it go away. The only way we can make it go away is a substitution. So I could use the substitution u is the square root of x minus 1. I don't think the substitution u is x minus 1 on its own now works. So you're forced to go to a square root substitution. Now, if you use the substitution, it will work, but you're going to get something which is improper, and you're going to need to divide or manipulate later on in the question. It's not a problem if you're good. You shouldn't really be having issues with that. But the best substitution for something like this is actually not this one. This is the one I'm going to use. I'm going to call u the entire denominator. How do I know that this works? I will answer you honestly, it's because I've done things like that before. As a student myself a very long time ago, of course I tried this a couple of times. I had problems. Other times I saw how to manipulate it, and then I realized when I saw deeper into the problems that this in fact is easier. So it comes with practice. Okay, so how will I use this substitution? Quite clearly, that's okay. It's going to be called u there. I need my dx. Do I write it x to the minus, to the half and differentiate it? You can, but you'd be better off to do the following. Subtract the 2 to the left. U minus 2 is equal to the square root of x minus 1. As I always strongly advise with square root substitutions, square both sides. Get rid of the square root first before you differentiate. So that's equal to x minus 1. Do you want to do implicit differentiation there? You can, but it's actually better to do something a lot simpler. Write it as x is equal to u minus 2 all squared plus 1. All I've done is I added the 1 to this side. Find your dx by du for all of this. This is just a simple chain rule, so it's going to be 2 coming to the front, u minus 2 to the power of 1, and the 1 will disappear. Lastly, you want your dx, and your dx is simply, let's write it explicitly, 2u, because it's to the power of 1, we can multiply the bracket, 2u minus 4, in a bracket, du. Okay, we're ready to go. Integral of 1 over. All of this, I called it u. So that's massively simplified. And on the top, or on the side, shall I say, I'm getting my dx, and my dx is 2u minus 4, 2u minus 4 du. Little bit of a tidy. That goes on the top, 2u minus 4 over u du. Split your fraction. 2u divided by u is simply 2 minus 4 over u, which I'm going to write like that because that integration to a log, du. Integration is finished now. 2u, which is respect to u, minus 4 log mod u plus c. And it's going to be a little bit messy to write my final answer. I almost tripped again on this cable, and my mic is going to be soon on my belly button because I keep stepping on the cable and I keep pulling it down. Hope it's okay, and I hope it's not making farting noises because it's very, very bad, this mic. It's really getting on my nerves. So 2, my u is 2 plus the square root of x minus 1 minus 4 times the log, and log of 2 plus x minus 1 plus c. I'm going to do two things in there because I like to do things properly. I don't need this thing anymore, so let me just rub it off first of all. Just purely for neatness. You shouldn't really lose marks in the exam if you leave this answer that I just put in there. First of all, this 2 times 2, when I multiply the bracket, is a constant, and I got more constants there, so I'm going to put it in the bin. I'm going to put it here and throw it away. So I'm going to write it as 2 times the square root of x minus 1, 2 times that. The 4, I've just put into the constant, I relabeled it. And also, I don't like to write this like this because this is always positive, and therefore it doesn't really need mods. Not that you really have to worry too much about it. If you leave it like this, it's still okay. Let me just see what answer I've got up there, by the way. I've got it, I left the mods up there, believe it or not, on my answer book. So this is in mods. It shouldn't do. This is always positive. Okay, that was number 113. 2 more to go. They're both very, very nice. I'm very, very pleased. Not deliberately done. I just followed the order in my book, and it turned out on this particular page, the last 2 to be very, very nice. It should take 1 minute each. 114. Integral of 4 over the square root of 6x minus 1. Please do not go for a substitution because you don't need it. Sometimes brain goes for very complicated things, although they're not needed. This is just a linear adjustment. You just need to write it a little bit differently. And this is of the form ax plus b. So it comes from a higher bracket, 6x minus 1 to the power of a half. That's the higher bracket. We differentiate it to adjust the constant. Half times 6 is 3. 4 divided by 3. Unfortunately, I cannot make it any better. So that's the answer. Or you can put square root. That's number 114 done. And number 115, I'm not even going to bother to rub the 114 because I don't need the space, is 3e to the 2x. And the denominator is e to the 2x minus 1. E to the 2x minus 1 dx. Actually, that looks very scary, doesn't it? It doesn't look too nice. How do we do this one? First of all, let me just say the substitution u is equal e to the 2x minus 1, not just e to the 2x, e to the 2x minus 1. Will work very, very quickly and very sensibly in about 3 or 4 lines. You'll have your answer. But this is of the type bottom differentiates to the top. and therefore the answer will be the log of this denominator with some number at the front. We just need to adjust the numbers. So if we differentiate this, we get 2e to the 2x on the top. We don't have a 2, we have a 3. That's not a problem. Numbers can be made. So the best way to perhaps do this, not the only one of course, is to write your denominator as it is, and this is what you desire to have on the top in order to apply bottom differentiation to top. But of course you need to balance it. It needs to be worth 3. At the moment it's worth 2. I don't know how many of you can see it. It just needs a 3 over 2 at the front. 2 times 3 over 2 gives you your 3 dx. And now this is perfect, and the answer is 3 over 2, the log of the mod of e to the 2x minus 1 plus c. And I think that is the answer. And that's the end of the lecture, lecture 10 up to example 115. And who's laughing now?